So, good evening, everyone. Welcome to the Problem Solving and Doubt Clarification course of NPTEL based on the topic Water and Wastewater Treatment. So, we are in week 5 now, like almost halfway through the course. As you all know, the course instructor is Dr. Bhanu Prakash from IIT Roorkee, and I am one of the teaching assistant for this course. My name is Akash Saha, and I am a PMRF scholar at the Department of Civil Engineering at IIT Madras, where I am pursuing my PhD in Environmental Engineering. So, we'll quickly go to the agenda of today's class. So, this week we have seen lectures regarding the food to microorganism ratio basically, and what is the relevance of it in our wastewater treatment plant design, and what are the different parameters, like the design parameters of the activated sludge process. So this is the activated sludge process. We are learning out of it for some time now, and then we looked into the sludge bulking and the variations we can have in the activated sludge processes. So we have step aeration method and other processes where we will fine tune some of the parameters, and we will try to increase the efficiency of the activated stress processes. Okay, and then we have also seen about the sequencing batch reactor, which is another variation of this activated sludge process, where we learned about the various components and the processes related to it. So we call it as SBR, and then we'll seen details about the nitrogen and the phosphorus removal, the different mechanisms, what are the different forms of nutrient in which they are found in the wastewater. So this was the whole content regarding this week's lecture. So I have some questions. So before solving those questions today, so I got some requests through mail that to show the derivation regarding the activated sludge process, because this is the main process where we need to learn about the design parameters and how to derive different different, like the HRT, the volume, the effluent uh, BOD concentration. So all those things are important. So what I will do, I will try to derive all the relations related to the activated sludge process, and then we will see all the questions related to it. So it will be easier for you to solve also. Okay, so I'll go to the text mode. I hope it's fine for you guys, because I don't remember who requested it actually, but it will be useful for you guys also. So we will see the basics of the derivation for the activated sludge process, and then we will solve the problems. Okay. I hope you are able to see my screen. So before going to the derivation, there are few parameters that we should know regarding the activated sludge process. I will quickly tell them. So let me ask you guys. So what do you mean by volumetric organic loading? So can someone tell me what is volumetric organic loading in an activated sludge process system, or any reactor for that matter? Like, in no need to give the relation, just the basic ideology behind it. So what do you mean by volumetric organic loading? So it is basically like how much organics are being given to the system per time, per day, whatever. So we will basically find it in the form of kg BOD per volume per day. Okay, so this is the basic unit, and we will calculate it as the inflow discharge into the BOD concentration, the influent BOD concentration, and we can convert it to kg, because most of the time it is in milligram per liter divided by the volume of the tank. So this is basically volumetric organic loading, because this can be a direct question. in your case in the MCQs, like find out the volumetric organometality. So we have to just find out how much mass of BOD is coming into the system per volume of the reactor per day. Okay, so like that we can find out. And then we have discussed this in the last class, like the F by M ratio, which is the food to microorganism.
Excuse me. Excuse me. This
Yeah,
10 raised by minus 3 is just to convert liter to
no, no,
meter cube.
it's for since BOD is mostly in milligram per liter.
Right.
Okay, so okay, yeah. So to convert into kg, we need to multiply into like divide by 10 to the power 6, and then from liter to meter cube again 10 to the power 3. So overall 10 to the power minus 3 will come. Okay. So both the things are taken into
So what
consideration.
will be the unit in this case?
What
Q
will be
into
the
B into 10 raised. What will be the units in this case?
unit will
Q
be
into
like
V.
we can say meter cube per second into milligram per liter divided by 1 by milligram we can say. So it will be mass like some milligram per per volume. It can be whether it can be in liters or meter cube per second or per day like that.
I don't understand 10 raised by minus 3 is per lot.
Uh, okay, so it's not necessary actually 10 to the power minus 3. It was just because I was saying since BOD mostly is given as milligram per liter. So if I want to change it to kg, I need to give it 10 to the power 6. Okay,
Yes.
and Q value is mostly given in MLD. Okay, so MLD is 10
Right.
to the power 6 liters, or I can write 10 to the power 3 meter cube. Okay, so now 10 to the power minus 6 and 10 to the power 10 to the power minus 6 and 10 to the power minus 3 when we multiply, it will give 10 to the power minus 3. So from here, the term is coming. So we'll get the answer in kg and in meter cube finally,
Right. Thank
like that. Okay, so you can neglect it. So based on your question, we can change whether it's 10 to the power minus 3 or, but mostly the standard units are like this. So we will use 10 to the power minus 3 directly. Otherwise, you can just neglect it. Okay, okay. So what I was talking about, I was telling about F by M ratio. So it is the amount of food that is kg BOD divided by the ml VSS I can say per day. So it will be just Q into BOD divided by V into the ml/VSS. So how much food you are giving per uh, per unit of microorganisms per day. So like that we can find out the F by M ratio. Okay.
you. Is this only influent BOD or we have to take into consideration effluent also? This
See,
BOD is influent.
mostly like this can be written as QS naught by Vx, or sometimes it is also written as QS naught minus S by Vx. So if the effluent concentration is given, okay, that some part of BOD is going out from the system after the aeration or after my secondary clarifier. So if that data is given, then the only food to be considered is the difference between the influent and effluent. Okay, but if that data is not given and if it is not known to us, then we can directly take just the influent part because that is the amount of available food to the microorganisms.
But why are we subtracting effluent? That is not food available. No?
Yeah, no, if that data is known, if I know my whatever effluent is going out of the system, that means that food is not like available to my microorganisms, right? It is anyway going out, flushing out from my system. Okay, so
Okay,
that much food we are not considering for our design.
okay, fine.
Okay. So it can be in both the ways, QS naught by Vs or QS naught minus SE divided by Vs. So we just have to see like how much data is given in the question and accordingly we can find it out. But I think this will be the most appropriate term, like if we know the effluent also. Okay. And the so okay, so these are the two basic criteria. Now we will go to the design part. So I will draw the schematic of this ASP at first. So basically, in that ASP, we have an aeration tank. So we have an aeration tank with a stirrer. So, so this is an aeration tank. The volume of the tank will be V. Okay. The amount, the volume of the tank will be V. And then we will have a secondary settling tank. Okay, so where all the biomass will get settled. So these are the two major components of this ASP. Now suppose the influent that is coming from the uh, primary sedimentation tank, the quality of that influent has the flow rate as Q naught, the amount of BOD that is present is S naught, and let's suppose the amount of microorganisms present uh, at first is X naught. So S will be always my BOD concentration or my food, I can say, or and X will be related to my microorganism. So these are the basic or standard notations that we will be using throughout S and X. So at in the influent we have Q naught, S naught, and X naught. Now, in the reaction, in the aeration tank, after the reaction or after the degradation of the biomass, degradation of the biological matter that is present in the system, the S naught will change to S. So this is my final effluent that is coming out from the system, and the concentration of microorganisms, let it be X inside the tank. Let it be X. Okay. Then it will go through this, and then some part will be coming at as the effluent. Okay, some part will be rejected from here, and also there will be some part which will be recycled. So these are the three streams that is coming out from the secondary uh, settling tank. So so basically, suppose the part that is recycled, that flow rate is QR, that is recycled back, because we need to maintain the microorganisms in the aeration tank. So some part of the biomass that is being settled in the secondary settling tank will be recycled back into the aeration tank. Okay, so suppose that is QR. Now the BOD will remain same throughout in this system because now there is no decrease. So S will remain as S, and the amount of microorganisms now they have settled. So a part of them we are recycling. So let it be XR instead of X. Let it be XR. Okay, and this wasted sludge, let it be QW, that is the flow rate that is being wasted. S will remain as S, there will be no change, and this microorganisms concentration will be the same, that is XR. Okay.
But S is being consumed by the microbes. So how the S will remain same?
No, see, we are just assuming that all my degradation of my biomass is happening in this aeration tank. Okay. So once my S naught is entering into the system, it is changing to S. It is changing to S. So that is the only degradation is happening to the BOD. Now after my like my biological matter or my BOD leaves the system from aeration tank, there will be no change in the BOD. That's what I'm assuming. Okay, because after that in the settling tank there is only settling is happening. There will be no what to say decomposition of this biomass or of this biological matter. Okay, so S will remain the same. I am assuming that my S will not getting like neither it will get increased or decreased. Nothing will happen to it. It will remain the same. Is it okay? Okay, so now the total flow rate that is coming into my aeration tank will be this Q naught plus QR. So the flow rate that will be leaving my system will also be Q naught plus QR. So the flow rate that is leaving from my aeration tank will be Q naught plus QR. Again, the BOD will remain as S, and the microorganisms that is also living will be X. So these two will remain because whatever in the tank we have seen that mostly in the any CSTR, if you say. So whatever is the concentration inside the tank, the same concentration will be the effluent what is coming out from the tank. Okay, so that's why S and X will remain the same here. So now, after all this, so whatever the leftover part that is coming out from the secondary effluent treatment tank is, the secondary effluent settling tank is Q naught by Q naught minus QW. So this is what it is left in flow rate, and this will be S. I will make the settling biomass here. S will be the same, and uh, the effluent microorganism that is coming, that will be very minimal, that will be, let it be XC, or the effluent microbial concentration. Okay, so is this clear, like all the notations? Is there any doubt in this, like all this notation that we have used here? Is this clear? Shall I go ahead, or is there anything else to? Yeah, please. I'm not able to hear you. Can you please increase your voice?
Are in recycling also and in waste also.
Yeah, so what is happening is, like, if I will draw this secondary settling tank. So this is the settling tank. So in this, what is entering is X. It is entering is X. So let it be, let I say 1,000 milligram per liter. Let it be 1,000 milligram per liter of X that is entering. So after settling, the biomass concentration with time will increase. Suppose it is more than that. Okay, so what is coming out from here will be, suppose, maybe 5,000 milligram per liter. Okay, and whatever will be left in the frozen, it will be much lesser. It will be much lesser, maybe 100 milligram per liter. Okay, so now this what is coming out from here, from the bottom, the same will be recycled back, and the same concentration will be wasted. There is no change. There are no division in this. Okay, so that's why both of this thing will have the same XR. Okay, these are just two flows. It is not like they are the concentration will divide or something. It will be the same concentration. Okay, am I clear?
Yes.
Okay.
Uh,
So
I
yeah,
think I have to rejoin. Is the screen visible? I think I have to rejoin.
okay. I will wait for a minute. You please rejoin. I will wait. Others, is there any problem with this schematic? Please react or give a thumbs up or something.
Yes, visible.
Okay, huh. Okay, so these are all my notations. Now we will see how to derive one by one thing after another. So if we talk about the steady state biomass mass balance. So first we will do the mass balance for the biomass, or the microbes. So we have the influent biomass. Some of the biomass will be biomass produced, and then it will be equal to my effluent biomass plus some wasted biomass. So these are all my streams which I have shown you. So how I can depict it? So my influent biomass will be nothing but Q naught into X naught. So the total influent biomass that is coming is Q naught plus S star. Now, how much biomass is getting produced? So, uh, with time, I can write it as dx by dt. So, dx by dt biomass is produced in V, because to maintain the same unit, because Q naught into X naught, what will Q naught will be liters into milligram per liter. So, liter will cancel, it will be milligrams. Okay, so everything will be in terms of mass. So now here it will be, or sorry, it will be meter cube per liter, not liter per second. So mass per unit time. So milligram per second. The unit is milligram per second. So here also dx will be milligram per liter, dt will be in second, and my to make the unit as milligram per second, I will multiply it with the another volume term. So liter will cancel. We will get mass per second. So biomass produced will be volume into dx by dt. And now the effluent biomass. What is my effluent biomass? That is Q naught minus QW into XE that we have find out. And my wasted biomass will be QW into XR. So this is my first equation. So I will write it as Q naught X naught plus V dx by dt is equal to Q naught minus QW XC plus QW XR. Okay. So this is my first mass balance equation. Now similarly, we will do steady state substrate mass balance. Steady state substrate mass balance. So what will be my influent substrate that is coming into the system will be again Q naught into S naught. So here instead of X, we will use the notation S. So it will be Q naught into S naught. Now here, like in the last term, we had biomass produced, but in this case, the substrate will be lost because it is getting degraded. So it will be minus V ds by dt. So there we had plus V dx by dt, but here since the substrate is being used up, we will have minus V ds by dt. Now again, the rest of the things will be same, Q naught minus QW into S, because S will remain the same, plus QW into S. So pretty simple, same as the above equation. So whatever, this is my influent, this is what is being used up with time, and this is my effluent, and this is wasted. So again, we have the equation Q naught S naught minus V ds by dt plus, sorry, equal to Q naught QW S plus QW S. So this is my second equation. Now we have to write an equation about the biomass growth. So biomass growth, which I denoted as dx by dt. Okay. So how we can write it? We can make use of the growth constant. Okay. With growth rate. So mostly this dx by dt, I will write it directly proportional to x. And in first order term, let there will be a constant of proportionality, so that will be mu x. So I will write dx by dt is equal to mu x. Mu is the my growth rate, proportionality constant, and some part will be getting decayed also. There will be a decay constant also. So it will be minus kd. Kd is my decay constant. So again, it will be first order. Kd is my decay constant into x. So it will be mu x minus kdx. So this is the net biomass growth that is happening in the system. Now what is mu? We have learned about the Monod's equation. So what was Monod's equation? Monod's equation was mu is equal to mu max s by ks plus x. So if we remember, this was the graph. The graph was something like this. So this was our mu max. I hope you know all these things. This is with respect to S, and what was Ks? So whatever was by corresponding to half of mu max by 2, that will be my Ks. This is the half saturation constant. Okay, so I will just simply write dx by dt is equal to mu max s into x divided by Ks plus s minus Kds. So this is my third equation, the biomass growth rate. Okay, is it clear till now? Anything to be discussed? Please stop me there itself and we can discuss. So I will just quickly go through the next thing. Now, after biomass growth, we have to also find out the substrate utilization. The substrate utilization. So substrate utilization means that we use that term ds by dt. So this is my substrate utilization. Now I will directly find in terms of minus because that is getting removed or used up. So it will be negative. So minus ds by dt. So I can write it as, now we know that I can write y as dx by dt divided by ds by dt. So what does this mean? This is the yield coefficient. Y is my yield coefficient. So how much microorganisms is produced per time per unit of my substrate used per time. So dx by dt divided by ds by dt. So, or we can directly write by x by s also. So whatever microorganisms were grown in a particular time available for the available food. So x by x. So how I can write ds by dt? I can write simply write 1 by y into dx by dt. So this is from this equation I am directly getting. Okay. And again, I will just simply put instead of dx by dt, I will write mu max s by ks plus s into x. So simply, instead of mu x, I have written mu max x plus ks by s into x. So this was about the substrate utilization minus ds by dt. Okay, so now in our first equation, so what was our first equation? This was my first equation. Now we will assume that in our system, this there is no inflow of microorganisms. So my x naught will become 0. We will assume that no microorganisms is entering into the system. And also in the effluent, no microorganisms are coming out of the system. So, so we will consider in this equation, in equation 1, that both my x naught term and my xc term will become 0. Okay, so whatever biomass or microorganism that is entering in my system is through the recycling, that is XR. So how my equation will change? So here both this term will get 0. So the only thing, so so we will assume x naught is equal to xc is equal to 0. So this is our assumption. So what will happen to equation 1? So my equation 1 will become as v dx by dt is equal to qw x star because the other two terms are becoming 0. Okay. So now we will substitute for dx. So now we will substitute for dx by dt because we know the dx by dt. So it will be v u max s ks plus s x minus k dx is equal to qw xr. Okay, I will just mention all the equation numbers again. Like this is equation 1, this is equation 2, this is equation 3, this is equation 4, Now this is my equation 5. This is my equation 5. Okay, so I will just uh, take the KD term to the right side. So what it will become, and V also the right side. So it will become, yes, Prashant, this video will definitely be posted in my YouTube channel. So you can directly see it from my YouTube channel. You can refer to this again if you want. Okay. But I don't think I can upload these notes anywhere. So you just go through the video and write it down whenever you have time. So Umax X into Ks plus S will be equal to Qr by Vx plus Kd. So this will become my equation 6. So I've just rearranged the terms. So this is via equation 6. Now further we can also write, okay, we can we can also write that further net growth of microbes. The net growth of microbes, that is dx by dt, can also be written as qwxr by v. So this will also give the net growth of microbes. How? Because qw again it is meter cube per second into milligram per meter cube divided by meter cube. Okay, so we are getting dx by dt. So this term is also equal to my dx by dt. So my dx by dt can also be written as qw into xr by v. Okay, so I will divide by 1 by x in both sides. So 1 by x dx by dt will be equal to qw xr by xv. Just dividing by x in both the side. Okay, so this is one thing. This I can write it as equation 7. This I will use it again. So that's why I'm just marking all the equations. Now, also again, I can write dx by dt. Here we are using this term again and again in various forms because we need to substitute in the final equation and get a very simpler one. So that's why we are doing all these things. So again, this can be also done as ds by dt can be also written as y into, I can write it as RST, that is the rate of substrate utilization. Okay, that is also I can write it as dx by dt. That is also we can do, but mm, okay. So we will write it as RSU. That is the rate of substrate utilization. Okay, rate of substrate utilization minus the decay constant. So we can write dx by dt in terms of this. Fine. So this dx by dt I will replace it from the, now from equation 7 I will substitute this dx by dt. So it will be qwxr by x is equal to minus y into rsu by x minus kd by vx, rather it will be vx. So I can write it in this form. Okay, so I have just uh, from equation 7 and dividing by x throughout. So we will get this simpler equation. Is this okay? So here we are getting a term like this. So if we find Vx by Qw into Xr, this is nothing but the mean cell residence time, that is MCRT, or what we call it as theta c. So this is one of the most important parameters in our system. Okay, so we can find this mean cell residence time, like how much time the microorganisms are there in my system. So this is one of the most important parameters for designing our wastewater treatment plant. So theta c. So whenever directly it is asking like find out the mean cell residence time, so it is nothing but Vx by Qw into Xr. Okay, and again you must be asking like what is RSU? RSU is nothing but how much food is the specific utilization rate, food utilization rate, that is ds by dt, something like this. And q by v, v by q I can write it as theta. So theta is my HRT. Okay, so like this also I can write. So again, if I want to, so let this be my eighth equation. So substituting my theta c in equation 8, I will just write it as 1 by theta c is equal to minus y into RSU by x minus kd. Okay, so this will become as by kd, and now I will substitute for RSU. So it will be 1 by theta c is equal to RSU I will substitute as S naught by theta x minus kd. So finally from here, we can again theta is equal to V by Q. So again we can find out the finally the volume of aeration tank. The volume of aeration tank V, we will finally get it as Q theta C Y into S naught minus S divided by 1 plus kd theta c into x. So this is my ultimate simplest equation. So from here we can find it as the volume of aeration tank, or anything. If we want to find x, we will just write q theta c y s minus s s naught minus s, then v into 1 plus kd theta c. Okay, so whatever parameters are given in your system, just we have to substitute and find out the corresponding other parameter which is not given. So this is the basic derivation of the wastewater treatment plant. Is it okay? Is there anything else to be explained again? Any term which you didn't understand? Shall I quickly go through it again from the second half, or is it okay, clear? Anyone?
Can you please repeat V, the volume of aeration
Volume
tank?
of, see, we got this equation, right? We got this equation. This equation we just got. So here the theta is nothing but the HRT. HRT is V by Q. So if we substitute V by Q here, we will get V into the equation, and then if we rearrange it, we will get V in terms of Q into theta C y S naught minus S by 1 plus KD theta C into X. So we'll get it is just rearranging. Okay, from there we are getting the volume of the aeration tank. It is directly we are getting from here. Just we have to rearrange and substitute this. Okay, because V will come in the denominator, we have to just multiply and divide and take it into the right side. We will get this equation. That's all. Okay, this all explanation and is getting recorded, and I will upload into the YouTube so we can anytime access it. Fine. And one more thing, this was regarding the microorganisms. Now, if we want to do the same thing for this substrate, so substrate mass balance. If I want to do the same thing, so substrate mass balance, we know this equation Q naught X naught plus V ds by dt is equal to Q naught QWS plus QWS. So this was our equation. Now we know that my ds by dt was 1 by y mu max Sx by Ks plus S. So this was my ds by dt. So I will simply substitute this ds by dt here, this ds by dt here. So on rearranging, we will get mu max Sx by Ks plus S is equal to Q naught y Vx into S naught minus S. This we will get. And on further solving, the final effluent, that is the final effluent S, I can write it as Ks 1 plus Kd theta C divided by theta C yk minus Kd minus 1. So this is another equation that we will get. Okay, so here my K, that capital K that we have got here, that capital K will be nothing but mu max by y. This is another notation which we call it as max rate of substrate utilization per unit mass of microbes. So mostly this capital K value is given in the questions. So that's why I've just substitute y max by y as capital K. So these are the two major equations. These are the two. This is B equation and this one A equation. This A and B are my two major equation to solve any problems related to this all this ASP, activated stress process. If you remember these two equations, most of the equations can be solved. Most of the problems can be solved. Okay, so we will solve some problems. We will get an idea regarding this. And if you have any doubts, you can get back to me. So now we will move on to the MCQ questions. Okay. So you please go through this derivation once again from my YouTube video or whatever you are, or if you have written down, you please go through it. If you have any doubt, you can get back to me over my email, or maybe next class you can ask the same. Okay. Hello.
Question.
Hey, Saket, are you saying something?
The last equation,
Yes. What happened?
final equation.
Yeah.
I want to say again.
Final question. Oh, 1 minute. Just a second. Okay, yeah, this was the equation.
I'm noting down it.
Okay, okay, note down, please. So shall we move?
Okay, sir. Thank you, sir.
Okay, okay, okay. So we will go to the multiple choice questions now. Okay, I hope you are able to see my screen. So this is the first question. It says that select the correct sequence of characteristic growth phases of a pure culture of microbes. So we have four options. So please tell me what is the correct sequence of characteristic growth phase for the microbes. So last class also I think we discussed about this. So you might remember the microbial growth phase. First there is some lag, then there is log growth, then there is a flat line, and then there is a downward steep. So what are all these phases? Anyone? B. Uh, no, Prashant, I don't think is the right answer. Okay, I will tell you again. So if you are just the number of particles, that is x, and time, if you plot a graph, so suppose the initial concentration is x naught, very less. So when we provide them more and more food, first there will be some lag. Like it will try to acclimatize with the surroundings. Okay, it will not start growing just by itself as you give food. So first time there is a acclimatization phase. It will get used to the system. It will get used to the environment. So this is called the lag phase. So what this is called? This is the lag phase. Okay. Now slowly it will start increasing and it will go exponentially. Or so this zone is called as log phase or the exponential phase. Then this exponential phase will start declining a bit. Okay, declining a bit. So this is the declining growth phase. It has started declining this growth. And after a point of time, the number of uh, microorganisms that is formed will be equal to the number of microorganisms that is lost or that is dying. So that will be stationary phase. So this is my stationary phase. And then after a point of time, all the food will be lost and the microorganisms will depend on themselves. They will depend on themselves or their own protoplasm. So they will go for cell lysis and then there will be an endogenous phase. So this is my endogenous. And this is my declining. This little small phase will be my declining growth phase. Okay, so I hope it is clear. It was a direct question. So it will be first the exponential growth phase. Here there is no mention about the lag phase. So first there will be exponential growth phase, then it will be declining growth phase, then it will be a stationary phase, and then the engineering phase. So whatever I explained just now, it is here. Okay, is it clear? We'll move to the next question. Now in the previous question, it is asked, in the endogenous phase, there is a little growth in the microbial dense population due to scarcity of substrate. So, is it true or false? So, the system is moving into the endogenous phase. That means they will depend more upon their own protoplasm or on the other microbes. Okay. So, it has to be true that there is a very scarcity of substrate. There is no more substrate is available. So there will be very little growth. Okay, the depth of the microorganism will be much more than the growth. So hence there will be a decline. So as far as this statement is concerned, it is true that there will be very little growth in the microbial population because of the scarcity of the substrate. Okay, so the answer is true. Is it clear? So both questions are connected. The endogenous phase is where low soluble BOD results in the loss in the viable bacterial cells, and most importantly, lysis of dead cells will happen. So this is about the endogenous phase. Okay, we'll move to the next question. Please try this question. This is much simpler. So it is asking about a typical flowchart of an SBR, sequential batch reactor. So we have pumping, decanting, sedimentation, aeration, and disinfection. So what is the correct order? Please let me know the correct order in the chat box.
It's B.
Okay, so two of you are saying it's B. Okay, so first it is pumping, then aeration, then sedimentation, then decanting, then disinfection. So B is the correct option. So what you have done? Pumping, aeration, sedimentation, decanting, and disinfection. Okay, so this is fine. Now next question. Sludge bulking. So here we are talking about bulking of sludge. Sludge bulking can usually be controlled by, you have to select the correct option or options. Maybe one option is correct, maybe two option is correct. So what is the correct answer? So is it by adjusting the F by M ratio, adjusting temperature, aeration, denitrification? A, B. Can you please explain
A
like
and C.
uh, see, I am asking like why by adjusting temperature we can reduce sludge bulking. Is there any reason? Like how by adjusting temperature we can reduce the sludge bulking. So actually there is no direct correlation. Okay, there is no direct correlation, and also aeration also there is no direct correlation. So only one of the option is correct that we are telling, that is adjusting the F by M ratio. So as in the videos also it is been it is been taught that there should be not neither very high F by M ratio or very low F by M ratio. We have to come at a very sweet spot. Okay. So it should neither be very high, neither be very low. So because if if the F by M ratio is very high, okay, so again more and more food is available, so there is a chance that filamentous bacteria will grow. Okay, so it cannot be very high and neither too low. So we have to adjust the F by M ratio only. So the correct answer is only option A, adjusting the F by M ratio. Whereas temperature, aeration, denitrator, there is no direct correlation of it. Maybe if instead of adjusting temperature, it is by adjusting the sludgeage or reducing the sludgeage, then yes, sludge bulking can be controlled. But uh, here the only answer is F by M ratio. Okay, the next question. Select the characteristics of biological system with a high F by M ratio. So what happens when there is high F by M ratio? Is there excess food for microbes? Microbes have low energy to swim around, good settling flux formation, or fast microbial growth rate. So I have to select the correct characteristics of high F by N ratio.
Excess food for microbes.
Excess food for microorganisms is one of the right answers because there will be more BOD, so more food. There is one more correct answer. Yeah, so as Prashant is saying, it is D is also correct because as more food is also there, so there will be a fast microbial growth. There will be a very fast microbial growth. So both A and B, or rather D, I have marked it incorrectly, it is D. So both fast microbial growth and excess food of the microorganism, they are the correct answers for this. Next question. What are the potential consequences of sludge bulking in wastewater treatment plant? Reduced treatment efficiency and increased effluent solids, increased energy consumption and operational cost, obstruction of pipes and equipments in the treatment process, all of the above.
Of the above.
All of the anyone else? So it's very direct question. It's all of the above because we have seen one equation by our instructor. It was 1 by theta c is equal to y into efficiency into F by M ratio minus KD. So if my efficiency is so due to sludge bulking, my efficiency will definitely get reduced, and also by there can be increased energy consumption, and also due to sludge bulking, some of the sludge can come out as effluent and then destroy the other pipes and equipments in the later stage. So all of the above is the correct answer. Now next question. What is the primary reason for bulking of sludge in wastewater treatment plant? So here also more than one answer can be correct. So is it excessive growth of filamentous bacteria, inadequate mixing of wastewater and sludge, high organic load and low MLVSS in the aeration tank, insufficient aeration in the treatment
A and
process?
C.
A and C. Yeah. So it is true, both of them are correct. Like excessive growth of filamentous bacteria can be a reason, and also there can be high organic load. Okay, and low MLVSS. So again, my F by M ratio will increase. So due to that, sludge bulking can happen. Whereas inadequate mixing is not the primary reason, and also inefficient aeration is also not related to it. So both A and C are the correct options. I hope others, the questions are very easy this time. So I hope others are also following. Okay. So I'm not discussing very much in detail. These are very simple questions. Okay, next question. Which of the following is not a variation of activated sludge process used for nutrient removal in wastewater treatment plant? So it is SBR, step aeration, extended aeration, or rotating biological contactor, which is not a variation of ASP. Prashant says it's D. Anyone else? So actually, it's right. It's only option D because other three are very direct variation of the activated sludge process. So only the rotated biological contactor is not a direct variation of the activated sludge process. Okay. Now the next question. Select the correct characteristics of nitrifiers. So here we have to identify the characteristics of nitrifiers. Highly sensitive to DO, less detention time than heterotrophs, highly sensitive to toxins. DO can be used as a measure to control nitrification and denitrification. A and C. Okay. What else? Actually, what you have said is correct. Both like highly sensitive to DO because these nitrifiers are very much sensitive to the dissolved oxygen concentration and also they are sensitive to the toxins present. So both A and C is correct. One more option is correct. Can someone tell? So actually option D is also correct here that DO can be used as a measure to control the nitrification and denitrification. These both are different process. One uh, so we can control what will happen in the system as per the DO concentration, nitrification and denitrification. So both all the three A, C, and D, all three are correct options. Now next question, it's a direct numerical. So we have to determine the effluent BOD of wastewater in a flow of 10 mld and the following design conditions. So number of tanks is 1, flow is 10, influent BOD S naught is 95, SE is no influent TSS. So suspended solids is 70. First order death rate constant is KD 0.05. Specific yield is Y is equal to 0.5. The mu m is 2.5, Ks is 115, and sludges is theta c. So we have to find out the effluent BOD, that is Se or S for that matter. So please try to find out. So we have seen a similar equations. We have derived it and done everything. We just have to put the correct values and we can find out the answer. So please let me know the correct answer. I will wait for some time. All the input parameters are given.
What does this influent TSS mean? The microbes are being added.
Sorry.
What does this influent TSS mean?
TSS is the total suspended solids.
But do they count for the microbes?
So no,
Are
microbes we will find out in terms of VSS. Okay, we will find out in terms of VSS, but maybe this is an additional info. So it may not be directly required to solve this problem. Or mostly TSS value we won't take for microorganisms concentration, we will take VSS value. I think in this question also they have done like this. We will check, we will see the solution, but I think this is an extra information. Okay, so we will see the answer. It is 8.65 milligram per liter. So we have just derived this equation. Okay, so as you can see in this equation, it is Ks 1 plus Kd theta c into theta c mu m minus Kd minus 1. So directly we can get the answer. So here, as I said earlier, that influent TSS is an extra information because mostly if you want to find the count of microorganisms, it should be given in terms of VSS. So even if TSS is given, we have to divide it by or multiply by the ratio, VSS by TSS ratio, and then we have to find out the VSS. So with the help of this equation, if we substitute all the parameters, right parameters, we will get the S value as 8.65 milligram per liter. So direct application of what we have found out. Now next question. Again, it's a numerical type and combined equation. So please note down the parameters. We will see one by one all the questions. So please note down the parameters as I speak. So we have a municipal wastewater treatment plant. It uses traditional activated sludge process. So the population of the village is 18,000. The sewage sludge generation per capita or per person is 200 liters per day. The infant BOD S naught is equal to 220 ml/VSS. So here ml/VSS is directly given. X value is directly given. 2800 milligram per liter. The first order death rate constant Kd is 0.05 per day. The specific yield Y is 0.5. Now assume that the PCB or the Pollution Control Board enforces a treated wastewater standard of 20 milligram per liter. So SE value is also given 20 milligram per liter and the suspended solids of 20 milligram per liter. So this is the data that is given for the question. So make a note of it. We'll see what are the questions that is asked. So the first question it is asked that if the volume of reactor is 325 meter cube, then the hydraulic retention time of the wastewater in the tank in hours to achieve the required quality of treated wastewater is.
You please show the question once again.
Yeah, I'm just discussing the question. So in the first question, it is asked that if the volume is 325 meter cube, volume is given, we have to find out the hydraulic retention time in hours. Okay, hydraulic retention there is theta. So I will again show the data. So V is 325 meter cube. We have to find the theta.
So the question.
Next question. Okay. Did you get the answer? Okay, so here if I would say the volume is given, V is given. Now to find the HRT, we need the Q because theta is equal to V by Q. So how will I find the Q? So here we have been given that the population is 18,000 people and the per capita sewage generation is 200 liter per day. So 18,000 into 200 liter per day will give me a value of the discharge. That much liter per day, or we can convert into meter cube per day. So if we directly divide V by Q, we'll get the answer. So I'll tell you the answer. So it is 2.165, but this is the solution. So my V is 325 and Q is 18,000 into 200 by 1000. So 1000 I am going to convert liters into meter cube. So you'll get 0.09 days or 2.167 hours. Okay. So directly we can get the answer. Okay, so we'll move to the next question. The average time for which biomass stays in the system is. So now the average time for which biomass stays in the system. So that means it is asking, can someone tell me what parameter it is asking?
Theta C.
Theta C. Okay. So please try to find out the theta C.
MCRT value.
MCRT or theta C. Okay, so here the answer would be 2.896. And how to get the answer? So again, we will directly use the equation. So this is the equation which we will use. X is equal to y by 1 plus kd theta c s naught minus s theta c by theta. So here everything is known except the value of theta c. Okay, every other parameter is known. So if we substitute all the parameters, we will get 2.896 days. Only theta c has to be found out. So this is the 12th question. Now last question. If microorganisms reach half of their maximum growth rate when BOD concentration is 120 milligram per liter, then the maximum growth rate is. So again it is asking that if the microorganisms reach half of their maximum growth rate. Okay, so here we have to connect through Monod's equation. When BOD5 concentration is 120 milligram per liter, then the maximum growth rate is. So we have to find mu max. And what is 120? Can someone tell me what is 120 given as? Just think about Monod equation and what are the parameters are there. So S it is saying that when S is equal to 120 milligram per liter, the microorganisms reach half of their maximum growth rate. That is, at S is equal to 120 milligram per liter, my mu is equal to mu max. So that means this value of 120 is the value for Ks. Okay. So the correct answer is 2.76, but here we will use this equation again. S is equal to Ks value, that equation. So there Ks term needs to be known because S it is directly given as per PCB, it is 20. So the only value that is not known is mu m value. So they have just uh, given it in a very different way, the Ks value. So are you able to understand that when S value is equal to Ks value, that is 120 milligram per liter, my mu max will be equal, my mu value will be equal to mu max by 2 as per my Monod's equation. So that was it is saying in the question. So once we get the Ks value, the rest of the parameters are already known. We will just simply substitute and the mu value can be calculated. Is it clear? Okay. Okay, so last two more questions are there. We'll quickly go through. So it says that facultative bacteria are able to work in presence of O2, absence of O2, presence as well as absence of O2, none of them. So
C.
option C. So it is a very direct question. Option C, presence and absence of O2. We have discussed this in the last class also, I think. Last question, match the following. So we have anoxic, heterotrophs, anaerobic, and autotrophs. So to match with the correct description. Just tell me the final answer. Option B, that is once see. So anoxic is the absence of only oxygen. So only oxygen is not the final electron acceptor. So instead of there, it can be nitrate, nitrite, anything. So anoxic condition is C, absence of only oxygen. Heterotrophs are those uh, organisms which use the organic sources as their energy. Yes, Saket? So
And B.
I'm not able to hear you. Your voice is not clear. Can you please write it in the chat box? I will see. Please type it in the chat box. Okay. So heterotrophs are those organisms which, yeah, B is the right answer. So heterotrophs are those organisms which will use the organic sources. Anaerobic is any electron acceptor like oxygen, nitrate, nitrite, nothing should be there. It is there will be no electron acceptors like this. The only acceptor can be the organic matter itself. Okay, and autotrophs are those which will depend on the inorganic sources. So option B is the correct answer. Fine. So these are all the questions which I had for today. So the next class will be on 1st March 2024, again on Friday from 7 to 9. So, and if you have any issues, you can connect to me in my email address
Skins of
saha19akash@gmail.com.
last question.
Yes, yes, Saket. Saket, your voice is not clear. Okay, thank you. If you have no more doubts or issues, you can leave the session.
Thank you so much.
Okay, thank you.
Slide. I want to take a screenshot.
For which, for what?
Please show the last slide. I want to take a screenshot.
Yeah, okay. Is it clear? Okay, so if you have no more doubts, you can leave the session.